So my today's session will be on the discussion of discrete random variable, expectation, and its variance. Okay. So I hope that you all are able to see my presentation. I have not uploaded this note yet in the Google Classroom. So after the class, I will do so. So this particular topic is very important for the understanding of all the remaining topics of the syllabus. Okay. Later you will understand why am I saying so. So we shall start discussion with we shall start our class with the discussion of the definition of random variable. Random variables are of two types. One type is called discrete and another type is called continuous. Okay, but whenever the board work is required, I will do the board. I will stop presenting the I will stop sharing this presentation and I'll go to the whiteboard and I'll do the board work. I can see that only 44 participants are present. Okay, but remaining participants are not, remaining students are not joining in. Now it has become 45. Anyways, so random variable, the definition goes like this. Random variable is not a variable which you can say that is a variable which takes values randomly. That is not the random variable. Rather, random variable is a function. It's defined to be a function from the set of all possible outcomes to the subset of set of real numbers. Random variable is a kind of function from the subset of set of real numbers, from set of all possible outcomes to the subset of set of real numbers, a special type of function. So this function is actually, to make you understand what this is all about, let me give you an example of tossing two unbiased coins simultaneously. Okay, or two coins, be it unbiased or biased, that is not a big issue, but I'm tossing two coins simultaneously. Now, once we toss two coins simultaneously, then you know that the possible outcomes are these: HH, HT, TH, and TT. Okay. Now, if I want to count the number of heads obtained in each of these outcomes, and if I want to, and let me denote this count of number of heads by capital X, then capital X can take several values. Several possible values are there which can be taken by capital X. Let us denote those values by small x. So capital X is the mother variable which can take different values at different points of time. And those values are small x. Okay, listen to me very carefully. What are the possible values of x? Now, as I'm saying that random variable is a function. Now you see, since I have designed capital X to be the count of heads, if I apply that count on the outcome HH, or if I put it in another way, that I'm counting the number of heads on the outcome HH, then this count is coming out to be 2. Same thing when applied on the outcome HT gives you the count 1 for the head. For TH it is 1, and for TT, since there are no heads, the count is 0. So in this way, you can design your count of heads on the outcomes obtained by tossing two coins. Similarly, another person can define another variable capital Y, which sorry, there is a mistake. It should be number of you just note it down. It is not number of heads, it should be number of tails. Before submitting the note, I shall rectify this particular thing. So number of tails, if I'm interested in number of tails, and if I denote this by capital Y, so in that case, if I want to count the number of tails in the first outcome, it is coming out to be 0. Number of tails in the second outcome, it is coming out to be 1. The number of tails in the third outcome, it is coming out to be 1. And number of tails in the last outcome, it is coming out to be 2. Just the opposite of what we have got earlier. And if I want to count the heads in the first coin only, And similarly, if you want to count the heads in the second coin only, or if you want to count the tails on the first coin only and the second coin only, so you can design your counts in several ways. So according to this, if I apply Z on the outcome HH, in the first coin, we have got only one head, and this is the only possibility. So I have written 1. In the second outcome, the count is 1 because only one head is possible in the first coin. In the second coin, in this third outcome, in the first coin, there is no head, so it's 0. In the last outcome, there is no head in the first coin, so it is 0. So in this way, you can define many such counts on the outcomes obtained by tossing two coins simultaneously. Okay. Now, these counts, so what we are actually representing? What we are actually representing? We are seeing that you see that I can say that if on your left side, you consider a sample space which consists of these particular outcomes, HH, HT, TH, and TT. On the right hand side, you have got a subset which contains the numbers 0, 1, and 2. For these two, you have got the subset 0, 1, 2. For the last one, you have got a subset 0, 1. So you can consider the variables capital X and capital Y to be the function which, when applied on the set of outcomes on the left hand side of yours, gives you some real numbers. In the first two cases, the real numbers are 0, 1, 2. In the third case, the real numbers are 0, 1 only. These real numbers I'm considering are discrete. Okay, no real numbers are lying in between them. So I'm considering these three discrete real numbers, 0, 1, 2 for the first two cases and 0, 1 for the third case. So obviously, if I consider the set 0, 1, 2, it is obviously a subset of set of real numbers. If I consider the set 0, 1, it is obviously a subset of set of real numbers. So therefore, in this case, we have got three different random variables. We have defined three different random variables. One is denoted by capital X, one is denoted by capital Y, and another is denoted by capital Z. So remember, random variable is a function defined on the set of all possible outcomes, or defined on the sample space, which gives image in the subset of set of real numbers. Okay, let me save the chat. Okay. Now, let us go to the next part. I have set a question. What is the question? Suppose that capital X is a random variable that takes on one of the values 1, 2, or 3. So these are the values now. Probability of X equal to 1 is 0.4. Okay, this is a separate problem. It is not related to the problem which is the example which is given above, because here capital X is not the count of it. It's not talking about the tossing of a coin. Capital X is some function which has been defined on the sample space, and which, when applied on the values of the sample space, on the elements of the sample space, gives values 1, 2, and 3. Now, probability of that capital X takes the value 1 is given to be 0.4, and probability that capital X takes the value 2 is given to be 0.1. What is the value or probability that capital X takes the value 3? Now, remember one thing. Suppose if I consider this particular example above, and if I ask you what are the probability, so forget about capital Y and capital Z. I am sticking to capital X only. And you have got these 4 outcomes and these 4 values, these 3 values, 2, 1, and 0. Now, if I ask you what is the probability of this, if I consider that these coins are unbiased, and if I ask you what is the probability of these outcomes, you will immediately say the probability of HH is 1/4, probability of HT is 1/4, probability of TH is 1/4, and probability of TT is 1/4. Or if I say that, yeah, I'm tossing a coin which is not biased, then also you can allocate the probabilities in this following manner. You can consider probability for HH to be half and probability of HT to be half, and these two probabilities are 0. Or you can put probability of HT to be 1 and all the rest of the probabilities to be 0. Or you can put probability of TT to be 1, all the rest of the probabilities can be taken to be 0, because I have told you that we do not calculate probabilities, we allocate the probabilities to the outcomes. So these things will happen in the case of biasedness. In all the cases, be it biased or be it unbiased, what is happening, you take the summation of all the probabilities. If I consider 1 4 1 4 1 4 1 4 4 times, it gives you 1. If I consider half and half, if I consider half and half for these two, it will give you 1. If I consider 1 over here and 0 for the rest, it is giving you 1. Okay, so in all the cases we are getting the total probability as 1. Why is it so? Because any sane person knows that when he tosses a coin, he is sure about the sample space. He knows that in the tossing of two coins, no other outcomes can appear other than these which are included in this set. So my sample space is complete sample space. So if my sample space is complete, and if I can make this kind of chart, that chart with outcomes and probabilities, this type of charts are called probability distribution. Okay, this type of charts are called probability distribution. So here, when they are giving this question to you, they are considering that they are dealing with a probability distribution chart where only 3 values can appear, 1, 2, and 3. And two probabilities have been given to you. One probability is 0.4 and another probability is 0.1. Now, the fundamental property of the probability distribution is that total probability must be equal to 1. So as I have already mentioned with respect to the above example, so if I consider this to be a complete chart, and that I must consider because nothing is mentioned, this chart is not complete. If nothing is mentioned, then I have to consider that yes, it is a complete chart. Then I can apply that rule, and I immediately know that since these are the only three possibilities for capital X, probability of that X takes value 1 plus probability of X probability that X takes value 2 plus probability of X takes value 3, that total probability must be equal to 1. So therefore, P of X1 plus P of X2 plus P of X3, that should be equal to 1. And therefore, from there, I am getting this. So probability of X equal to 3 will be 1 minus probability of X equal to 1 minus probability of X equal to 2. I am substituting these values over here, and thus I am getting the probability 0.5. Here I am applying the property that the total probability in a probability distribution is actually 1. Okay. Now I'm putting the things with respect to I'm putting a graph, and there I'm showing you what is happening over here. So you see that I'm plotting the sample space on the x-axis and the probabilities on the y-axis. I'm marking the points 0.1, 0.4, 0.5. These are the probabilities. I'm marking the points which are outcomes 1, 2, and 3. And since probability of X equal to 1 is 0.4, so I am putting over here 0.4, and then I'm dropping a line which is hitting it is a straight line which is perpendicular to the x-axis, touching x-axis at X equal to 1. And thus I'm also plotting the other two probabilities. For X equal to 2, I am plotting 0.1, and for X equal to 3, I am plotting 0.5. This particular graph is called probability distribution, graph of the probability distribution. Now, someone wants to say something, I think. You can unmute yourself and you can ask if you have any question, because you have raised your hand. Oh, I think it is by mistake. Now, I'm stopping the share for the time being. I'm going to present the whiteboard. There, I'm going to write one particular property which isn't mentioned in the note. So you note it down. So The point is that when we talk about probability distribution, and if we declare that the distribution or the chart is complete, that means we have considered all possible outcomes then the probabilities present in the chart are called probability mass function. Probability mass function. Okay, or in short, they are known as PMF. Now, all the probabilities with respect to the coin tossing problem, that is 1 by 4, 1 by 4, 1 by 4, whatever, these are actually PMFs. Okay, the probability mass function is always associated with discrete probability distribution chart. Discrete probability distribution chart. Okay, and for continuous probability distribution, similarly, we have another case where probability distribution is continuous. Their probabilities present over there have a different name. They are not known as probability mass functions. So when I say that I'm dealing with probability mass function, you should immediately understand that I'm talking about a discrete probability chart. And these PMFs have two properties. These PMFs have two properties. What are they? One property is this probability of capital X equal to small x, or sometimes it is denoted by small p suffix x. This is always non-negative, and this is property number 1. And property number 2 is probability of x equal to small x over all x. This is equal to 1. Or sometimes it is also written as summation over x px is equal to 1. So we can use this notation or that notation. Okay, so these are the two fundamental properties of probability. Discrete probability, these are the fundamental properties of probability mass function associated with a discrete probability chart. Okay, now let us get back to the original PDF file which I was sharing with you. Now, what comes next? Let us see. Then I have set one question which goes like this. I want to calculate the expectation and variance of the random variable. Now, random variable, you know, is a kind of function, and that function, this function that I have designed over here with respect to the problem of coin tossing, that is capital X or capital Y or capital Z, whatever it is. For them, I want to calculate the expectation. So expectation and variance are actually calculated with respect to the expectation of the function will be calculated, the variance of the function will be calculated. So let's see how it happens. Okay. Now you see that I have considered here the problem which I have just now solved. The problem, question number 1. In question number 1, we have the values x equal to 1, 2, and 3, and the probabilities are given. So I have considered this chart and I have put it in the form of a table. This is called the table which I have got is called the probability distribution or probability chart. So I have put the value of x, which is 1, 2, and 3, and the probability of these variables of this variable capital X for different values is 0.4, 0.1, 0.5. And since the total probability is 1, so this chart is complete. Proper probabilities, and I have already told you that these probabilities are probability mass function. So you see that if probability mass, this probability, if we denote probability of capital X equal to small x as probability mass function, then these probabilities are always non-negative, as I have already told you, and total probability must be equal to 1. Now, what do we mean by the expectation of the random variable? First of all, let me talk about the technicality of these two terms, expectation and variance. Okay, first of all, let us try to find out how to calculate this expectation of discrete random variable capital X and variance of the discrete random variable capital X. Okay, let us try to know the formula first, and then I shall explain what actually I am doing. The expectation of the discrete random variable capital X is actually denoted by E of X, EX, and is defined as all the values which are present in the probability chart, which we denote by small x, those values will be multiplied by their corresponding probabilities, and all such products will be added together. That is called the expectation. So you look at this definition carefully. So x here is the value which is present in the probability chart. Probability of x equal to small x, p of x equal to small x is the probability of that particular value. Now I have this chart with me. Okay, now this is the value x equal to 1. Okay, so I shall multiply the probability 0.4 by 1, or the value will be multiplied by its corresponding probability. The second value is 2, so its probability is 0.1. So we shall multiply the value 2 by the probability 0.1. The third one is 3, and this is the value, and that will be multiplied by 0.5. So if I do so, and if I add this product, I will get the expectation of the random variable as 2.1. What is variance of the random variable? How it is calculated? Now, the variance of the discrete random variable is calculated as follows. It is denoted by Vx, and it goes by the formula Vx equal to Ex square minus Ex whole square. Ex you have already found, which is 2.1 with respect to the given problem. Now, what is the formula for Ex square? Now, Ex square has this formula. Only difference between Ex and Ex square is that here probabilities were multiplied by the value. Here probabilities will be multiplied the value squared. So x squared will be multiplied by the probability, and we'll take the sum. So we have, thus we have got Ex squared as 1 squared into 0.4 plus 2 squared into 0.1 plus 3 squared into 0.5, which is 5.3. Now, this is the value of Ex square. This is the value of the Ex square. And since Vx is Ex square minus Ex whole square, so we shall subtract 2.1 squared from 5.3, and the result will be, the outcome will be 0.89. So thus, with this formula, we can calculate the expectation of the random variable and variance of the random variable. But the question is, what is happening over here? What do we actually mean by the expectation and variance of the random variable? So let us try to find this out. I hope that you know a little bit of mathematics. Okay, a little bit of statistics. You have come to know a little bit of statistics from your school days. So by hoping this, I think that you know this particular thing which I'm writing right now, that I'm writing x equal to small x. These are the values, and f of x is equal to small x, or sometimes it is written as just f of x. Okay, what are these? This is called the value which is associated with the system, and this is called the frequency. So I have actually considering a frequency chart. I am actually considering a frequency chart. Okay, what is the frequency chart? What is frequency? Frequency gives you the count how frequently value appears in the system. So for example, I'm taking an examination, and 30 students have got 25 out of 25. Then how many students have got 30? 30 is my value. 30 is the mark. And if I want to count how many students have got 30, means how many times 30 appeared in the chart, that is called the frequency of 30. Okay, so thus we can identify all the values and the number of times they appear in the chart. That is called the frequency. So frequency means how many times or how frequently if the value appeared in the chart. That is called the frequency. Okay, now probably you can recall that when we talk about frequency chart, the arithmetic mean is actually denoted by x bar, and for frequency table this goes by the formula summation over x into fx whole thing divided by summation fx, okay, over all x. Or if you want me to write it explicitly, this is the value multiplied by the frequency, the value multiplied by the frequency plus the value multiplied by the frequency. If I consider there are n values, which will be divided by the total frequency, f1 plus f2 dot 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 fn. This is, I think you can recall this particular definition. Probably you have studied it. Arithmetic mean formula everybody knows. Now let us replace all fx by p of x equal to x. I am replacing the frequency by probability. So what will happen? I will get a probability chart. Okay, so let us write this probability chart. So you see, I'm writing the values x equal to x, and instead of writing the frequency, I'm writing the probability. Okay, if I do so, and if I declare that, now I'm declaring that my chart is complete. I am declaring that I have considered all the values present in the sample space. All the values present in the sample space. Then you know from the definition of probability mass function that in this case total probability px, that will be equal to 1. Now if I want to calculate the arithmetic mean, in this case the arithmetic mean will be x bar, which is equal to summation x into probability of x equal to small x over x, this divided by summation probability of x equal to small x over x. But you know, since the chart is complete, this probability is 1, and therefore this is equal to summation x x into probability of x equal to small x. Okay, which is nothing but the expectation of the random variable capital X. So when we calculate the expectation of the random variable, we are actually calculating the arithmetic mean of the function. So expectation is nothing but the mean of the function which you are calculating. Okay. Now, what about the variance? Now, when we talk about frequency chart, when we talk about the frequency chart, we are not only interested in calculating the arithmetic mean, but also we are interested in calculating the variance also. So variance is the measure of distance, is the measure of dispersion. Variance is the measure of dispersion. Okay. Suppose all my students have sit for statistics examination and they have performed and I have got their marks, and also I have calculated the arithmetic mean. So arithmetic mean actually gives a pillar. I'll calculate the percentage, that is the arithmetic mean, that is the pillar, and I'll say that around this pillar, my students' marks are scattered. Some are more than that, some are less than that. Some are very near to that. Now, if I want to calculate how much they are deviated from this particular figure, how much the marks, I'm talking about the marks, how much they are deviated from the pillar, that deviation, the measurement of the deviation is one of the best measurement of the deviation is by variance. And variance is calculated by the formula. If the frequencies are 1, it is given by the formula. Okay, for frequency chart, it is given by the formula summation fx x minus x bar by summation fx. This is the formula. Okay, and if I want to write it explicitly, then you can write it in the following manner: fi into xi minus x bar summation over I. Say I goes from 1 to up to n by total frequency. Okay, so this is the formula of the variance in case of frequency distribution. But when we replace frequency by probability, you already know that this denominator part will vanish, and the variance of the random variable, will then be summation over x. The probability will be replaced by this frequency, will be replaced by the probability. So probability of x equal to small x, and the value will be x minus ex, because x bar is my ex. This thing can be written in the following ways. We can write it as summation over x into px equal to small x, and we can write it as summation p of x equal to small x e of x. Okay. Or one thing I have to consider, or I missed it. This should be equal to squared. This is squared, xi minus x bar whole square. Otherwise, that will vanish. You know, sum of the deviation taken from mean will always vanish. Sum of the deviations from mean always vanish. Okay, so there will be a square term over here, so that will be a square. So let me do the mathematics once again. For simplicity, I can write this probability of x equal to small x by simply px. Okay, so we have got this as summation over x px, and this is x minus ex whole square. Okay, and now I'm going to break the square. So we get it as follows. This becomes x squared minus 2x ex, and this becomes plus ex whole squared. And if I try to find out the, if I take the product of these terms with the probability, what do I get? Let us see. We get summation x into px over x, and that is ex. And the last one is summation x px into e of x whole squared. Now I'm writing over here. So we get this is equal to the, so variance of x, v of x becomes x squared minus, now you see this total probability is 1. This total probability is 1, and ex is the constant. It can come outside the summation sign. So it is 2 into ex, and summation x into px is nothing but ex itself by definition. And here ex squared, since ex is the arithmetic mean, and arithmetic mean is always constant, it can come outside the summation sign. So I am taking ex squared outside the summation sign, and total probability summation over px, that becomes 1. So ultimately what you are getting, we are getting minus x squared minus 2 ex squared plus ex squared, and that is equal to x squared minus ex whole squared. Okay, now this excess, this this thing, one thing I have to, one more thing, I have done a little bit of mistake over here. This x squared is variable, so it cannot come outside the summation sign. So we have to put it inside the summation. Sorry. Now that is x squared px, and by definition, this will be equal to your ex squared. So it will be ex squared. Sorry, it will be ex squared, and thus you get the formula of the variance. Okay, let us continue in the next session because the time is almost over for this session. You take a screenshot quickly of this page.